In this video, I'll cover word sense disambiguation. I'll provide an overview of the topic and then discuss some baseline techniques for performing word sense disambiguation. After that, I'll discuss how contextual embeddings and feature-based methods can be used to improve upon those techniques, and close by introducing the Lusk Algorithm, a classic baseline for word sense disambiguation. Word sense disambiguation is the task of, perhaps unsurprisingly, disambiguating between different senses for a word. For example, if I tell you, I'm going to withdraw some cash from the bank, you can probably deduce that I'm referring to a financial institution and not the side of a river. It's actually quite tricky for computers to do this. When you're trying to determine how to perform word sense disambiguation for your own tasks, there are a variety of things that you need to consider. For example, different types of tasks have different sense tags, and these sense tags might also vary depending on your task domain. If you're performing automated indexing of medical articles, you'll probably want to disambiguate things based on their medical subject headings, which would probably not be nearly as useful if you're performing machine translation. If you're just trying to disambiguate a small number of words, then small, traditional, supervised classification techniques tend to work well. But if you're trying to disambiguate all words in a large text, you'll probably need to build larger and more complex models. To train word sense disambiguation models, you can leverage large existing manually tagged corpora like SemCor, various corpora from the sense-eval tasks, and certain corpora from past sem-eval tasks. The task of word sense disambiguation in general is framed such that, given a word in a test set, you need to select the correct sense of the word, given all possible senses in either some sort of domain-specific tag set or in a larger resource like WordNet. There are a few surprisingly strong baselines for word sense disambiguation. One is simply to choose the most frequent sense for each new word, based on counts from some labeled corpus. Another is to assign the same sense to a given word every time it appears in a given text sample, based on the premise that people usually retain the same sense for a word throughout a single discourse. However, we may in many cases want to achieve performance beyond what these simple baselines can deliver. In those cases, we can make use of modern contextual word embeddings. Contextual word embeddings are similar to the word embeddings we already discussed in earlier modules. However, the values in the embedding vector differ across different senses of the same word. For example, the financial version of bank and the river version of bank would not have the same word embedding. A very high-performing solution leveraging contextual word embeddings is actually quite simple. To train the model, you extract a contextual embedding for each word in your sense-labeled training set, so SemCor or whatever you're using, and then average the contextual embeddings of all instances associated with each word sense to create sense embeddings. To test the model, you then compute the contextual embedding for your new target word, and then just find the sense embedding that has the highest cosine similarity with that embedding. Of course, using that approach, some words won't have sense embeddings since there are inevitably going to be some words that didn't exist in the sense-labeled training corpus. To address those cases, you can fall back to the most frequent sense baseline, or you can compute the missing sense embeddings using more sophisticated methods based on the sense embeddings we do have, coupled with our knowledge of the WordNet hierarchy. In some cases, we may not want or need to use contextual word embeddings. Perhaps we're working with a very small data set for our task, or perhaps we have limited computational power. Fortunately, feature-based approaches to word sense disambiguation work almost as well as contextual embedding-based approaches. Common features to use in feature-based word sense disambiguation models include part-of-speech tags, unigrams, bigrams, trigrams, or, if you still want to incorporate word embeddings to some degree, the weighted average of embeddings for words preceding and preceding the target word. You can then just pair those features with a statistical classification model of your choice. All of the word sense disambiguation approaches we've discussed so far have relied on manually labeled sense corpora. However, creating those corpora is quite costly and time-consuming, and there may be many languages and text domains for which those corpora are simply not available. In those cases, we can rely on knowledge-based approaches to word sense disambiguation instead. Knowledge-based approaches make use of existing external knowledge sources, such as WordNet, rather than relying on supervised machine learning. One classic and very popular knowledge-based approach to word sense disambiguation is the Lusk algorithm. The Lusk algorithm selects word senses based on dictionary glosses, with the intuition being that the gloss for the best sense will share the most words with the surrounding context of the target word. The formal algorithm for the simplest version of the Lusk algorithm is shown here. We first initialize the best sense to the most frequent sense for the given target word, the maximum overlap to 0, and the context to the set of all words in the sentence surrounding the target word. We then loop through each sense associated with the target word. Within the loop, we set the signature variable to the set of words in the gloss and in the example sentence or sentences corresponding to that sense. We then find the number of words in common between the signature and the context, ignoring stop words. We check to see if overlap is greater than our current maximum overlap, and if it is, we assign this overlap as our new maximum overlap and this sense as our new best sense. When the loop terminates, we return the best sense. It's very simple to visualize what this looks like, and we can see that from the example here, reproduced from the course textbook. Let's say we have an example sentence. The bank can guarantee deposits will eventually cover future tuition costs because it invests in adjustable rate mortgage securities. We want to disambiguate the word bank. We also have the word net senses here for two different senses of the word bank. One is referring to the financial institution sense of the word, and the other is referring to the Riverside version of the word. We can see that sense number 1 has 2 overlapping words with the provided context. On the other hand, we can see that sense number 2 has 0 overlapping words with the provided context. Thus, we'll go ahead and choose sense number 1.